Designing for balance is core in competitive games. Ensuring fairness in player versus player games is a design goal that any game that features this sort of interaction should, at least to some amount, strive for. Unfortunately, it often happens that the whole of the possibilities given to a player exceeds the designer's expectations, creating combinations and exploits that sometimes threaten the game's reliability as a balanced and competitive title. Focusing on searching for an automated solution for avoiding infinite combos, one of the main flaws of fighting games, this work discusses the use of hidden Markov models to predict if a subset of inputs would result in a combo, as well as trying to predict the most likely outcome of a sequence of inputs. Both supervised and unsupervised learning algorithms were applied. Because of the excess of noise and particularities of the implemented model, we were not able to successfully predict combos. Despite that, our discussions in the matter and our findings are presented in this paper, and should be relevant to this overall discussion. A hidden Markov model is a statistical Markov model in which the model system is assumed to be a process with discrete time intervals, observable states, and unobservable hidden states. The model is used to predict the probability of a sequence of hidden states when given a sequence of observable states. To accomplish that, it utilizes the Markov assumption that the future does not rely on the past, as all past information is coded within the present. These types of models are especially known for estimating patterns of sequential information such as speech and handwriting.
Are you ready? Fight!
To even attempt to approach the problem, we needed a fighting game where we could simply input a player's commands and get whether the opposing player is stuck in a combo state or not. The first part is relatively easy. The second, however, would require us to get information stored within the game's variables, and not many games allow for this sort of intrusion. There are very few fighting games that are open source or moddable to the extent that we needed, and for that reason, we decided to continue our research on a fighting game of our own making. The game was adapted to this project by changing the player controller input to an input file containing the commands at every frame for player 1, and also to an output to a file at every frame writing whether player 2 is in a combo state or not. To optimize training and execution times, the game was stripped of most of its graphical and sound resources and had its overall speed increased. Any game will require player inputs, as it is necessary for the most basic interaction level. As this is the most common information the algorithm may ask for the player, regardless of the type of game being played, we believe that it is also the most generic set of information upon which a model can be built. One advantage of taking such a broad approach is that, if successful, it could be applied to any other fighting game as long as every action is deterministic. When a player makes an attack, he is unable to make another action for a number of frames. This happens since every attack animation has a period of cooldown associated with it. During this time, most of that player's actions are restricted, with very few exceptions. As such, whenever an attack is made, the player can expect to be unable to act for some time. Likewise, when a player is hit by an attack, he is also denied of actions for a short amount of frames during his damage animation. If a player that hits an opponent with an attack manages to attack again before that opponent may recover from the last hit, we call that sequence of attacks a combo. However, if the opponent is able to recover during that interval, we say that he was free. This, however, does not imply that players do not give any inputs to the game while they are unable to act. It is quite the opposite. In order to make a special move, an attack that is usually more powerful than a standard move, the player needs to give a sequence of inputs in a row, and this is more easily done during the time that the player cannot make another action. Because of this, between two significant inputs, there are a lot of insignificant ones that do not result in actions, but do have a free or combo state associated to them due to the opponent's latent state. These inputs are categorized as noise. During the execution of the game, there are two kinds of information that can be evaluated: the input of the player and its effect, which can be seen as the opponent's state. Since we were able to extract both sequences from the game's execution, we have two possible models. In one of them, we observe the opponent's state, and in the other one, we observe the player's input. The Markov chain for each of them can be seen in this figure. In the first scenario, each input is a hidden state. By training this HMM, we are able to learn the likelihood of each input resulting in a combo, and which inputs often follow another. In this representation, we are able to answer questions such as, which is the most likely sequence of inputs that result in a combo of a certain number of frames. In the second one, the hidden states are combo and free. Training this HMM results in different conclusions. Given that an opponent is in a combo, we can learn the likelihood of each input to be a part of that combo. With this, we can answer whether a given sequence was likely to be a combo and how many frames it had. We manually wrote 47 different possible combos, including what we believe to be the longest combo within the game. lasting roughly 240 frames or 8 real-time seconds. Next, we created 10 variations of each combo, containing noise for each noisy input. Along with these 470 now possible combos, we also randomly generated 1500 input sequences. All these 1970 sequences were then executed through the game, in order to get the sequence of states for each one of these sequence of inputs. Since we have all the combo, free, and input sequences, we chose to train our HMM through the supervised method. Given its simplicity and the lack of any prior knowledge representation, it far outshines the unsupervised approach, requiring only a few seconds to execute. The problem with this kind of algorithm is the need of labeled data, which can be difficult to acquire, but is not the case in our problem. We proceeded to execute 2 instances of our HMM and train each one with a different set. The first one was trained only with the 470 manually generated combos, and the second one received all the 1970 sequences. The objective of this particular experiment was to observe the HMM behavior when faced with the nearly complete chaos of the full training set. The HMM of the smaller and well-behaved training set functions as our control group. The resulting HMM was fed to the Viterbi algorithm, and we queried for the most likely sequence of inputs. Both of them returned the same response, although with different probabilities. One of the reasons this occurred is because when generating the game, both players are unable to do any actions for the first 5 frames of the game. Because of that, the first 5 inputs of the game are always 5-, which means stay still, which causes the starting probabilities to be 1 for 5- and 0 for all other states. Not only that, but the transition matrix heavily favors the transition 5- to 5-. However, since the Viterbi algorithm takes into account the emission probabilities alongside with the transition probabilities, this does not explain why 5- was selected, as staying still should be associated to the free state and its emission probability should be close to 0 and 1. Taking a closer look at a segment of the emission probabilities, we start to see the problem. Although the probability of 5- being free is higher than it being combo, so is the probability of everything else. Because of the noise inserted, the probabilities of each inputs seem to converge at 0.25 and 0.75. There are a couple of odd things though. When counting to the 0 to 1 ratio in the files, we conclude that roughly a third of the states are 1s, which should lead to the probabilities being 0.33 and 0.66. The other one is why the inputs 8- and 9- and also 7- behave differently from everyone else. During the generation of the random combos, there are no moves including the 7 or 9 directional. This was made in order to avoid the player from moving away from the enemy. There were, however, inserted as noise in the 470 combos. Because of this, they follow the 0.33, 0.66 trend of the file. As for the input 8-, the answer is quite simple. In the 470 combos created, a large sum of them involve jumping to start a combo. Because of that, there is this shift in probabilities toward the 0 state since the combo didn't start yet, and the player needs to go a few frames up to arrive at the desired height before attacking. The probabilities related to 8- being the state 1, however, are caused by noise. And train our HMM again, as expected because of its abundance in the 470 combos, the most likely sequence becomes this. The last question is why do movements like 2- have the same probabilities of attacks such as 6M? As explained before, when a significant input is given, the character that a player is controlling starts on animation. However, its effects are not atomic. It takes a couple frames for the attack to actually land. This makes an attack such as 6M to be treated as 0 even though it resulted in a combo later on. Because of the frame the action was made, its opponent's weight was 0. The other attacks in a combo were treated normally though. This explains why the probabilities of attack inputs being lower than they should. The first move of a combo is always 0, and it potentializes insignificant sequences to be marked as 1s. We then begin another experiment of a couple changes. First, we only train over the 1500 random inputs to avoid unwanted tendencies. Second, we remove the first 5 frames of each sequence to avoid the 5- in all inputs. Third, we hard-code the starting probabilities to be equal. The third step should not be needed given the law of big numbers, but we wanted to be sure. Although the sequence for the combos seems promising, looking at the sequence of frees show that these predictions are nothing more than wild guesses. Indeed, when looking at the emission and transition matrices, we can easily conclude that. In order to try to improve the obtained HMM, we run the Baum-Welch algorithm over the HMM trained with the 470 examples, using only the states of the written combos, but using all of the examples. The shorter one converges rather fast, only requiring 2 iterations in about half an hour. The longer one, however, did not converge after over 100 iterations and over 40 hours of training. Because of that, we decided to omit these results as they are likely poor. The probability of staying still increased drastically towards 0 and jumping upwards followed the same pattern. All inputs, however, showed an increase in the probability of a combo. Although this seems to be a good improvement, the most likely sequence continues not being a combo. Also, inputs like 2' and 4' also showed an increase in combo probabilities, which showed that the model as a whole did not improve much. Through application of a supervised HMM and also an unsupervised HMM, we realized that the effects of noise and delay were severe enough to overshadow the true patterns that led to combos. These implications assure us that inputs do not serve as a modeling criterion even when described under a sequential learning algorithm. The Markov assumption process suggests that the future is independent of the past. In our case, this does not apply, as the observation of the following frame depends mostly on a hidden state somewhere in the past. We could specialize the algorithm to avoid these flaws, or even try to predict the far future from a past frame instead of trying to predict the following frame. But since this diverges from the input approach, it leads us to believe that the input approach is not a reliable modeling basis in the first place.